Welcome to the deep dive. We're not just, skimming the surface today. We're really going headfirst into blockchain. It sounds maybe a bit intimidating, but honestly, it's changing everything. How we track goods, how we manage digital trust. It's pretty big. We all hear the buzz, right? Usually it's just crypto headlines. But underneath all that hype, there's this really foundational tech, much broader implications. So for this deep dive, we've looked at this really comprehensive guide. It's framed around top interview questions for blockchain software developers. But don't let that developer part put you off. It's actually a great shortcut, not just for people looking for jobs, but really for anyone who's curious or maybe prepping for a meeting. It helps you grasp the deeper architectural stuff and the actual real-world impact. Our mission today. Yeah. Let's move past the basics you might already know. Let's unpack the critical distinctions, the maybe surprising insights that make this tech so revolutionary. Okay, let's peel back the layers. Let's really get into what underpins this whole digital frontier. Let's start right at the beginning, but maybe with a slightly different angle. When we talk blockchain, what exactly are we talking about? Beyond just a distributed ledger, what makes it fundamentally different from just, a huge shared spreadsheet?
Yeah, that's a great starting point. Because what's really fascinating and often misunderstood is that while lots of people jump straight to Bitcoin, the core innovation isn't just about digital money. At its heart, blockchain technology is, yes, a decentralized distributed ledger system. But the real insight isn't just that it's distributed, it's how it records data across all these different computers in a way that guarantees security, transparency, and crucially, immutability. It fundamentally re-architects how we actually establish and maintain trust online. We move from trusting a middleman to trusting the math and the network itself.
Right, and I guess that's where the Bitcoin connection comes in, because it's so heavily associated with crypto. But our source material makes it really clear pretty quickly that the applications go way, way beyond digital cash. So what are some of the maybe more surprising places, even counterintuitive places, where blockchain is making a real difference, outside the obvious finance stuff?
That's a great question. Because the truly profound shift isn't just finding another way to send money. It's about creating a verifiable, tamper-proof record for pretty much any kind of data. Take supply chains. Imagine tracing, say, a diamond or even just a head of lettuce right from the farm to your plate. Every transfer, every quality check recorded forever on a blockchain, immutably.
Wow. Okay.
It's not just efficiency. It's about proving it's real, proving it was sourced ethically.
Right, authenticity.
Exactly. Or think about healthcare. Patient records could be secured, but still instantly available to the right doctors or providers. You, the patient, could have more control over your own data, but with strict privacy maintained. It's really about building trust and accountability without needing some central, potentially fallible authority figure.
Okay, that makes sense. So now we've got that foundation, what blockchain is. But it seems pretty clear that not all blockchains are the same thing. I keep hearing about different flavors or types. How do these different structures, serve different needs? And what are the big trade-offs when you choose one over another?
You're absolutely right. It's definitely not monolithic. And the source details, 3 main types. Each one is designed for different levels of access and control. This is where the nuances really matter.
Okay.
First, you've got public blockchains. These are what most people think of. Open to everyone, totally permissionless. Anyone can join, see transactions, often even help validate them. Bitcoin and Ethereum are the classic examples.
Right, the big names.
Yeah. Their strength is maximum decentralization. Censorship resistance.
Right.
Because no single entity is in charge. But that openness can sometimes mean challenges with, say, how fast it runs scalability and maybe less privacy for transactions.
Okay, so there's a trade-off there.
Definitely. Then you have private blockchains. These are restricted, permissioned, usually run by just one organization. Think of a company using it for internal records, maybe, or a specific group. They offer much faster transactions, more privacy, because, you control who gets in.
Yeah.
But you trade off some of that pure decentralization. The trust model changes from trust the crowd to trust the organization running it. And finally, there are consortium blockchains. These are kind of a hybrid. Semi-decentralized, they're controlled by a pre-agreed group of organizations.
Like a club.
Sort of. Imagine a group of banks, maybe competitors or logistics firms. They need a shared, trustworthy ledger, but nobody wants to give full control to just one company.
Gotcha.
So they get some decentralization benefits because there are multiple players involved.
Yeah.
But also the efficiency and privacy that comes from it being a known, permissioned group.
So, okay, if I'm getting this right, The choice isn't just about which one is best. It's about what's best suited for the job you need it to do. It sounds like a real balancing act. Decentralization versus control, privacy versus performance.
Okay.
And a public chain gives you that maximum openness, but maybe it's slower or less private. Private and consortium chains give you more control and speed, but you lose some of that truly trustless nature.
Precisely.
It really shows blockchain isn't some one-size-fits-all magic bullet. It's adaptable. Depends if you need total transparency or something more managed, maybe for enterprise use.
That's it, exactly. You're matching the core strengths, security, immutability with the specific needs for sharing data and governing it in different situations. A public chain might be perfect for a global crypto project, but totally wrong for, say, a regulated industry sharing sensitive data just among partners they trust. That whole permission versus permissionless thing is really the key distinction. It dictates who can do what, and it changes the whole trust model.
Okay, that makes sense. So we've got the secure distributed ledger foundation, but how do we actually automate things on this stack? Like agreements or processes, I keep hearing about smart contracts. Are those the key to putting blockchain into real action? And I mean, if the code is law, like people say, what happens if the code itself has a bug or some kind of loophole?
That's a really sharp observation, because yes, smart contracts are the automation engine for a lot of modern blockchains, especially platforms like Ethereum. They're basically self-executing contracts. The terms of the deal are written directly into the code itself. They run on the blockchain, and they automatically enforce and carry out those terms when certain predefined conditions are met.
Yeah.
It cuts out the need for intermediaries to oversee things or verify or enforce the agreement.
So kind of like that vending machine idea. You put the money in, hit the button.
Exactly. Conditions met, product dispensed automatically. No cashier needed. But you've also nailed the critical risk. If that code has a bug, well, then the bug becomes the law on the blockchain.
Uh-oh.
Yeah. The immutability, which is usually a huge strength, means that once you deploy a smart contract, changing it or fixing it can be incredibly hard, sometimes impossible.
Wow.
So that creates huge challenges around making sure they're audited properly, secure, how they're governed. It's a super powerful tool, but it demands extreme precision when you create it, because the code is the agreement. No takebacks.
So the power is massive, cutting out middlemen, speeding things up, making it transparent. But the responsibility for perfect code is huge because there's no undo button once it's out there on the chain. That really does raise big questions about the future of, traditional legal deals, financial agreements, moving from human trust and interpretation to, well, cryptographic certainty, for better or worse.
Exactly. It's a total paradigm shift. We're moving from trusting institutions to trusting math and hopefully really well-written code. The implications are profound. Think about insurance. Claims can be paid out automatically if certain verifiable things happen, flight delays confirmed by data feeds, weather events recorded.
Right, instantly.
Or real estate. Property deeds could transfer the second payment clears, cutting out weeks of escrow and lawyer fees. The challenge, like you said, is making sure the code actually reflects what people intended and that it's tough enough to handle anything unexpected.
That actually leads nicely into another critical piece, how these blockchains actually work and stay secure. Consensus mechanisms. These sound like the real engine room, deciding how everyone agrees on what's true. Our source talks about two big ones, proof of work, or POW, and proof of stake, POS. What are the fundamental differences? Not just the energy use everyone talks about, but how they actually achieve security, and what are the trade-offs for things like decentralization and speed?
Yeah, these mechanisms are absolutely foundational. They determine how a decentralized network agrees on which transactions are valid, which blocks get added. They're essentially solving that classic computer science problem, the Byzantine generals problem, in a distributed system. How do you agree when you can't fully trust everyone?
Okay.
So with proof of work, POW, you have participants called miners competing. They're trying to solve these incredibly complex cryptographic puzzles. The first one to crack it gets the right to add the next block of transactions to the chain, and they get rewarded for it.
Like a race.
Exactly. But this race needs immense computing power, and therefore lots of energy. Its security comes from the sheer cost of trying to cheat. It would be astronomically expensive to get enough computing power to maliciously rewrite the chain history. You'd have to outcompute the entire honest network.
Makes sense. Very hard to cheat.
Right. The trade-off, though, as we've all heard with Bitcoin, is that energy consumption is massive. And it can limit how fast the network operates scalability, because solving those puzzles takes time.
Okay, so that's POW. What about proof of stake?
Proof of stake, POS, takes a totally different approach. No massive computational race. Instead, validators are chosen based on how much cryptocurrency they stake, basically. Lock up as collateral in the network.
So skin in the game.
Precisely. The more coins you stake, the higher your chance of being picked to validate the next block.
Right.
And if a validator tries to cheat or acts maliciously, they risk losing their staked tokens. That's a powerful economic disincentive. POS is widely known for being vastly more energy efficient. No need for that brute force computation. It generally aims for better scalability, lower transaction fees. Now, there are some debates. Does it lead to more centralization, where the richest players have the most influence? Does it create different security vulnerabilities? But protocol designs actively try to mitigate those risks.
So the contrast is pretty stark then. POW is like this digital arms race, security through massive computational cost, which, has those huge environmental questions. I remember headlines comparing crypto networks' energy use to small countries.
Those are very real concerns.
Proof of stake shifts to an economic game theory model. Security through financial commitment, aiming for efficiency. It's fascinating how they tackle the same problem, trust and security, but with totally different strengths and weaknesses, especially in that blockchain trilemma of security, decentralization, and scalability.
Absolutely. And those environmental worries about POW, they're a big driver. The move towards POS by major networks, like Ethereum did with the merge, shows a clear industry push toward more sustainable, scalable solutions. Each system makes different compromises across that trilemma, like you said. POW often prioritizes security and decentralization, sometimes at the cost of speed and energy. POW tries to boost scalability and efficiency while keeping security and decentralization strong, though the way it achieves decentralization is different. And the search is always on for even better, faster, more secure consensus methods. It's a really active area of R&D.
Let's dive into one of those core technical bits that makes a lot of this security possible. Often mentioned, maybe not fully grasped, the hash function. It gets called a digital fingerprint. Why is it so vital? What does it actually do to make the blockchain tamper-proof?
Okay, the hash function is basically a mathematical algorithm. It takes an input. Any input could be text, a file, or in this case, a block of transactions.
Right.
And it spits out a fixed size string of characters. That's the hash value.
Fixed size.
Always the same length, regardless of the input size. And critically, the same input always produces the same hash. But, and this is key change, even one tiny bit of the input, just one character, and the output hash changes completely, unpredictably. It's also a one-way street. Easy to calculate the hash from the input, but practically impossible to figure out the original input just by looking at the hash.
Okay, so unique in one way. How does that secure the chain?
Its crucial role is ensuring data integrity. It gives each block a unique identifier, linked cryptographically. Each new block contains not just its own transactions, but also the hash value of the previous block.
The link.
Exactly, that's what creates the chain. Each link is tied cryptographically to the one before it, all the way back to the first block. Now, here's why it's so powerful for tamper-proofing.
Yeah.
If someone tried to go back and change any data in an old block, even change one comma,
The hash would change.
instantly, and it would be completely different. But the next block in the chain still holds the original hash of that block. So the link breaks. The chain doesn't match up anymore. Tampering becomes immediately obvious to everyone on the network. It's really a cornerstone of blockchain's immutability, that resistance to being altered.
Wow. So it's not just a fingerprint. It's like a fingerprint where if you smudge even a tiny part of an old print, the whole sequence of prints just falls apart digitally. That's a really powerful image for how it guards the history. Without that crypto link, the whole idea of an unchangeable record just collapses.
Indeed. And what's really remarkable is how this relatively simple cryptographic tool forms the absolute bedrock of blockchain's trustworthiness. Without strong hash functions linking blocks like that, you couldn't secure the chain cryptographically. The integrity of the whole ledger would be gone. It's really an elegant solution.
Okay, we've covered a ton of the foundational theory now. The decentralized idea, the different types, smart contracts, automating things, consensus, keeping it secure, hash functions, gluing it together. Now, how does all this theory actually come together in the real world? Through something called decentralized applications, or DApp apps. This feels like where the rubber really hits the road, right?
This is absolutely where theory becomes tangible utility, where we see the potential beyond just, digital coins. The source material talks about developing apps using platforms like Ethereum, languages like Solidity for those smart contracts we discussed. But it's more than just writing code. It's about building applications that actually run on these decentralized networks, using all the features we've talked about.
So what kinds of things are I talking about?
Well, imagine a social media platform where you actually own your data and your content, not the company running it.
Interesting.
Or a truly fair, transparent voting system. Every vote recorded immutably, auditable by anyone, no fear of tampering. Or even those complex, decentralized finance DeFi protocols, offering lending, borrowing, trading, all without needing traditional banks as middlemen.
Right. DeFi is huge now.
Yeah. These are the kinds of services dApps are starting to build. And there are specific tools developers use. Truffle, Remix, Infura are common ones to help build, test, and deploy the smart contracts and the user interfaces. It's a bit like traditional web development, but the back end is this decentralized network.
So all these building blocks, the ledger, the contracts, the consensus, they let developers create these new kinds of services. It really is taking the promise of blockchain beyond just currency and into actual applications that could change how we use the internet, manage assets, maybe even govern online communities. It sounds like rebuilding parts of the web with trust baked in from the start.
And if we connect that to the bigger picture, dApps are genuinely extending blockchain's reach far beyond digital money. They're sparking innovation, creating entirely new economic models by allowing services to run without a central boss, basically, giving users more control, more transparency. This is where that vision of a truly decentralized web, what people call Web 3, starts to feel real. It could fundamentally redefine how we interact online, how we think about data ownership, how digital services are governed.
Okay, so wrapping this up, what does this all really mean for us? We've gone through the core pieces. Blockchain as this decentralized ledger, secure, transparent, immutable. We looked at the different types, public, private, consortium, and why you'd choose one over another. We saw smart contracts automating agreements via code, but also the risks if that code isn't perfect. We dug into consensus proof of work versus proof of stake, how they secure the network differently, the energy debate, scalability, and the vital role of hash functions, those cryptographic links ensuring data integrity, all leading to real-world apps, starting to rebuild services we use daily.
And understanding these foundations, it's not just about knowing the buzzwords. It's really about grasping the core architecture of a technology that's fundamentally changing how we approach trust, how we manage data in our digital lives. It's a pretty robust framework, honestly, and it looks set to underpin a lot of our future digital infrastructure.
So for you, our listener, maybe think about this. How these core ideas, immutability, decentralized agreements, smart automation, aren't just abstract tech concepts. They're quietly reshaping whole industries right now. Finance, logistics, healthcare, impacting everything from how transparent your food supply chain is to how secure your personal data might be online. What do you think that really means for who or what you trust in the digital world? And how might these changes actually give you more control over your own digital life in the years ahead? Lots to think about. We'll see you next time for another deep